Let's take a look at this example. In 1990, the residential energy use in the U.S. was responsible for 962 million metric tons of carbon dioxide emissions. By the year 2000, that number had risen to 1,182 million metric tons. First, if the emissions are growing exponentially, find the annual percent increase. And second, once we get that, if the emissions continue growing at the same rate, what will the emissions grow to by 2050? All right, so the key word here in part A is exponentially. So let's recall the form of exponential growth. And you may use different variables than this, but let's say we've got some amount after a certain amount of time intervals. That's what this sub n is going to mean. The way that we would get that amount is we'd start with some initial amount. I'm going to call that q sub 0. And we would multiply that by 1 plus the rate increase. If it was a decrease, this r could be negative. That would be fine. And then we're going to take that to the power of however many times this increase or decrease is happening. So let's put our information over here into a little table of what we know. And let's label it n and q sub n. Those are sort of our inputs and outputs of our function. And we also have some years here. Let's put that down. So we know in 1990, the emissions were 962. And then I'm just going to make a note here that this is going to be million. I don't want to write all those zeros. Metric tons. And then in 2020, that number is going to grow to 1182 million metric tons. So now we need to decide. I don't want year 0 to be the literal year 0. So I'm going to make 1990 my starting year. So I'm going to make that n equals 0. You can actually make any year n equals 0. You just have to decide what that's going to be and be consistent throughout your computation. So then 2020 would be 10 years later. So n would equal 10. Now when we get to part B and we're trying to find 2050, the emissions, how many years is that after 1990? That's going to be 60 years after 1990. So the n value will be 60 in that case. All right, so if we go over here to our formula, we've got 1, 2, 3, 4 variables. I want to really highlight the fact that these two things go together. All right, those are the two things in the chart. It's like a data point. All right. And then the rest of the things, the starting value and the rate, are fixed throughout the whole growth process. But what we're trying to find is the rate. We don't know the rate. So we're trying to find this rate. So we're going to have to plug in values for q sub 0, which is this guy right here. All right. Actually, it's just the 962. It's not the 0 part. It's the actual population. And then we're going to have to plug in some point, some n q sub n. Well, that's where this guy comes in. All right, we're going to plug this n q sub n into our formula, and then we can solve for r. All right, let's do it. So I'm going to say after 10 years, the emissions were 1,182 million metric tons. They started at 962. I don't know what the percent increase is, but I know this 1,182 is after 10 years, so I have to plug the 10 in. Okay, so now it's just algebra from here. Depending on the level of your algebra skills, I'm going to go through solving this. If you're really good at solving this, you can kind of bloop, bloop, bloop ahead. The first thing I want to do is divide both sides by 962. That part's not too bad. Now, I don't really want to get the decimal for this because it's going to be ugly and I'd have to round it. And then the more rounding I have to do, the more inaccurate my answer becomes. So I know it's maybe a little unsettling for some of you, but I just want to leave that as that fraction for now. I'm just going to punch everything in all at once. Okay, so now this might be the new part for some of y'all. How do I get rid of this exponent? That's the next thing I do. I cannot... I'm going to erase this in a minute. Don't write this down. I cannot subtract that 1 out from under there. Because of the order of operations, I have to take to the 10th power everything in here. I can't just subtract that 1 out from under there. Can't do that. Okay, I have to get rid of this 10 first. So how do you undo taking something to the 10th power? Well, you have to take the 10th root. Now, a lot of you are maybe used to taking the square root. Like, let's say you had something like, I don't know, 25 equals r squared, and then you take the square root of both sides. And so you get 5 equals r. The square root undoes a square. Well, in order to do a 10th power, you have to do what's called the 10th root, which literally means what to the 10th power is. All right, so the 10th root. So I have to do the 10th root of both sides. Okay, so on the left-hand side, again, I'm just going to leave this, and we'll come back and talk about how to put this in your calculator in a minute as soon as we're done getting r by itself. Now, on the right-hand side, the 10th root and the 10th power, those undo each other, and so I'm just left with 1 plus r. Now, I can subtract that 1 from both sides, and my final undecimaled answer is this thing. Okay, so now we need to talk about how to put this into your calculator. So let's take a look at a calculator. On this calculator, if I want to do a 10th root, I have to put the 10 in first and then hit math and then go down to option 5. Now, for some of you who don't have a fancy calculator like this, you may see a button that looks like this. Okay, that's the button that you're going to need. And probably what you're going to have to do is Google your calculator and then say taking a root, okay, and see how you do that on your calculator. Oops, I hit on. I don't want to do that. I want to enter. So here on this calculator, I do this, and then I do 1182 divided by 962 equals, and then I'll go ahead and subtract 1, and that gives me this answer right here. Now, I don't want to round this too much, so I'm going to go 0.0208. All right, r equals 0.0208. If you have a calculator, kind of a simple calculator, maybe like this, another way that you can do a 10th root, and you may or may not know this from your high school exponents or whatever, 10th root is the same thing as taking something to the 1/10th power. All right, a cubed root would be the 1/3 power. A 5th root would be a 1/5 power. And so you probably have a power button on your calculator. So you, like, this is a power button right here. Okay, so I could go 1182 divided by 962, get that number, take that number to the, now I have to take it to the 1/10th power. So 1/10 is 0.1. I could just type in 0.1, or if I don't know the decimal, then I do parenthesis 1 divided by 10. So I'm taking it to the 1/10th power, see up here, equals, and then subtract 1 equals. So mess around with your calculator and see if you can get this value. If you can't, reach out, Google it. Okay. So our rate then, if I'm thinking of my rate as a percent, my rate as a percent is going to be 2.08% increase. All right, let's go over then and answer part B. So we have our formula, Q sub n equals Q sub 0 times the quantity 1 plus r to the n. We figured out the rate of increase. We need to put it back in the decimal form for this equation, 0.0208. And now we want to answer the question, let's use a different, how about purple? This one right here, all right? This is what we're trying to figure out. So we're going to put 60 in for n, and then we'll be able to figure out the Q sub n that goes with that n. In other words, the emissions. What are the emissions after 60 years? So 1 plus this would just be like that. 60, and now all we have to do is punch this in. So let's go for it here. 962 times 1.0208 to the 60th power equals 3,308.38. Should we do that? It's hard to know where to round sometimes. Remember, this is million metric tons, so when we're rounding, we're literally rounding off millions, so we want to be careful here. Let's go 0.375. So 3308 3308.375 million, and this is million metric tons. So we could actually take this decimal, because we've got 4 decimals. We could move this decimal 3 places over and write it as 3.308375 billion metric tons, which is probably a better answer. All right, so hopefully that helped you figure out like how to solve for r in these types of exponential change problems.